Selamat pagi, Bapak, Ibu, dan rekan-rekan sekalian. Kembali berjumpa di Kolokium Fisika Kuantum BRIN. Kolokium ini rutin diselenggarakan setiap 2 pekan sekali, menghadirkan pembicara dari internal Pusat Riset Fisika Kuantum maupun dari pembicara tamu di luar BRIN. Perkenalkan, saya Heski yang akan memandu acara hari ini. Topik yang disajikan dalam Kolokium Fisika Kuantum ini berbagai macam ya, cukup beragam dari fisika partikel, fisika material, informasi dan komputasi kuantum gitu ya. Dan kita akan membahas penelitian-penelitian yang up to date tapi dengan bahasan-bahasan yang pedagogis ya. Harapannya semua bisa memahami. Dan kali ini kita akan berbincang tentang ya quantum algorithm, quantum machine learning gitu ya, dengan pembicaranya adalah Mas ya, atau Bapak Gekko Budiutama. Beliau merupakan researcher di saat ini di University of Tokyo ya, benar ya. Dan ya, specially appointed researcher dan juga research scientist di startup yang bernama Quemix ya. Sebelumnya beliau merupakan postdoc di Tokodai dan juga mengambil PhD dan master di Tokodai juga, Tokyo Institute of Technology. Dan saya ketemu dia merupakan adik kelas saya waktu itu saya S3, Gekko S1 ya waktu itu di Tokyo University. Oke, mungkin tanpa berpanjang kata lagi, silahkan Gekko bisa mungkin lanjut memperkenalkan diri atau lanjut langsung dengan materinya. Silahkan.
Oke, selamat siang. Nama saya Gekko. Saya akan mulai sharing slide saya. Oke, apakah slide saya sudah tershare?
Oke,
Uh,
sudah.
Bagaimana sih? Oke. Jadi hari ini saya sebenarnya mau bicara pakai bahasa Indonesia, tapi saya tidak punya waktu prep time yang cukup, jadi saya akan membawa pembicaraan ini pakai bahasa Inggris. Jadi saya akan mengubah language yang saya akan gunakan sekarang. So, this talk will be in English, and what this talk will be is basically described in this slide. Your questions can be in English or Indonesians. And if you have any questions, you can just cut me in the middle of my talk and just shoot the questions. And this talk is for general audience with no prior knowledge in the fields of quantum computing, machine learning or AI, and quantum machine learning and AI. And so, if you're already deep into these fields, then it's probably not going to be very useful because it's a very general knowledge for general audience. And the last point is basically the same thing. The nature of this talk will be pedagogical. So for deep understanding towards the subject, please reverse to different papers and textbooks. And you can ask me about the necessary textbooks and papers as well. Yeah, today's title will be Attention Mechanisms for Quantum Neural Networks. But in the slides, I will expand a bit from the definitions of quantum computers and then the current trend of machine learning and AI, and then how those two fields interact with each other, quantum computers and machine learning and AI. And finally, I will start to talk about attention mechanism for quantum neural networks. So this title can be deceiving a little bit. And the content of this talk is partially published in my latest paper around 2 months ago, so Physical Review A. So if you have any interest, probably you want to dig deeper, you can just refer to this paper. So Mas Leo has already introduced myself, already introduced me to the audience. So my name is Gekko Budiutama. You can call me Gekko. I'm a research scientist at University of Tokyo and Quemix. I'm from Jakarta. My education is as listed here. And so, yeah, Quemix is basically a startup company started by one of my professors. So we're trying to develop different quantum algorithms mostly for material simulations, but we're also trying to expand our scope to machine learning as well. And my responsibilities in the University of Tokyo is pretty much the same. Basically, my responsibility is to develop this quantum machine learning or quantum artificial intelligence, and to see how quantum computers can kind of supercharge the current AI trends or machine learning trends. And so, yeah, that's basically the responsibility is pretty much the same. And let's get started with the presentations, the list of content. So as I mentioned, I will talk about the broad stuff, started from quantum computing, and then I'll enter to machine learning and AI and the introductions of quantum machine learning or quantum AI, or at least how these two interact, quantum computing and AI. And then I'll easily narrow down to quantum neural networks and how my research can improve quantum neural networks with something called attention mechanism. So brief introductions to quantum computing. And so, well, human race has tried to develop different hardware and software for computations for the longest time. So since the ancient time, we have abacus. And then after the industrial revolutions, we have analytical engines. It's basically computers that use steam engine. So it's kind of cool, like retro kind of computers. And around 1950s or so, the first digital mainframe for digital computer called ENIAC is actually, uh, what do you call it, deployed into the wild, basically. But ENIAC itself is not microprocessing, it's not powered by microprocessors. And so as you can see here, there are a lot of cables in which electricity have to go from different points of the terminal. And actually microprocessors are the ones that has been powering our digital lifestyle today, mostly CPU, but also lately, especially if you're gamers or if you're scientists, GPU has also been quite useful for a lot of different applications. And CPU and GPU are today's basically engines that drive our digital life, and also as well as, like, if you're a scientist, uh, basically they're the engines for our quantum simulations. And well, some of you probably have been very familiar with supercomputers. And for those who are not, supercomputers is basically, they're just your laptop out like a million times. There are a million of your laptops connected efficiently, connected in a smart way, uh, so that they can calculate something that your laptop will not be able to do. So that's basically what supercomputer is. And well, as you probably noticed, this point here is still missing. So a lot of people smarter than me argue that quantum computer will be the last inventions for the last computer that we will invent, because it's very hard to go even below that in terms of physical phenomenon. And so I would like to agree with that argument. And so I put the quantum computers as the pinnacle of our computing technologies. And quantum computers, shown here, quantum computers are shown here. So there are different types of quantum computers today. The most famous one is probably superconducting quantum computers developed by Google and IBM. And they're very beautiful. They're very eye-catching. And they have this, what do you call it? Chandelier-like, it's like a beautiful old lamp. And that's one of the reasons why probably they're very popular, right? They have been pictured in a lot of popular culture productions as well, such as film or movies, etc. But there's actually more than one approach to quantum computing, and some of which are listed here. There are also trapped ion quantum computers. So this is by a company called Quantinuum. I think it's UK-based company. There's also photonic quantum computers by Canada-based, if I am not mistaken. And lastly, neutral atom quantum computers by company QEra. So this one is MIT-based, if I'm not mistaken. So today, quantum computers, when we're talking about quantum computers, we're talking about these different approaches that essentially calculate the same thing. But unlike microprocessors that has been for the longest time using silicon semiconductor, for example, there's still not a single-minded approach to quantum computers. The jury is still up. Still, there are still different approaches to the quantum computing. And well, what makes quantum computers quantum? So the first reasons why quantum computers are different from, let's say, extremely huge supercomputer is because quantum computers utilizes these properties, this phenomenon that no matter how big your classical computer is, cannot be reproduced using classical computers. So the first properties is superpositions. And superpositions is just basically multiple states that exist at the same time. And so, well, why is this important, you might say? And I'll try to answer that questions using this example. So say you have a database. Well, it doesn't have to be a database. Say you have a jar, and within the jar there are 4 bowls, right? And on each bowls, something is written on each bowl. So like there's for the gray bowls, there's cow, there's apple, there's fish, and there's also lettuce. And so the task is now to find the bowls in which it mentions a vegetable. Well, we obviously know that it'll be this one, right? But well, let's see how classical computers try to solve this problem. Well, in classical computers, you solve this problem by, well, you pick one by random. Let's say by chance you take apple, and by clever algorithms, we are going to decide that apple is not a vegetable, which is correct, right? And then you pick another one, which is cow, and you run again the algorithms, and it's still not a vegetable. And you got another one, fish, still not a vegetable. And lastly, when you get the last bowl, which is lettuce, and the algorithms correctly notice that it's a vegetable. So this is how classical computers solve search problems. So you're basically uh, doing one by one examinations on each possible answers and try to find an algorithm that is good enough to mark whether the questions is answered or not. But quantum computers does this differently. So superpositions allows quantum computers to pick all the bowls just from the get-go. Cow, apple, lettuce, fish. And then what quantum algorithm will do, it will mark the correct answers by, let's say, in these examples, changing the size of the bowl. So at the beginning, the size of the bowl are all the same. And with clever quantum algorithms, quantum computers will increase the size of the correct answer. So this is actually a common approach for quantum algorithms. And well, as you can see here, you need only run the algorithm one time, whereas in classical computers, you are going to need to at least run it 4 times, and just to be safe, right? Just to be safe that there's no other vegetables on the database. And so these parallel examinations allowed by superpositions is one of the reasons why quantum computers will be extremely powerful. But it's not all sunshines and rainbow. There's also another quantum properties that quantum computers has that makes it actually kind of worse compared to classical computers. So for example, probabilistic nature of the quantum computers means that the outcome is not deterministic, rather a likelihood of all possible outcomes. And so, well, why is this important? I'll try to explain it using this example. So, well, this is a very easy mathematical questions. What is 2 plus 1? Well, classical computer, if you take your calculators and you put 2 plus 1 on your calculators 100 times, you will get 100 times 3. You will get 3 for 100 times, right? So classical computers only returns the correct answer. Well, you can try this at home if you don't have anything to do. You just put 2 plus 1 100 times. It'll always return 3, which is the correct answer. Well, with quantum computers, this is not the case. So the answers of quantum computers will look something like this. So with the correct algorithm, it will return 3 the most time, but it will also return other like 1, 2, or 4, or 5 at different times. So this probabilistic nature of it. So for example, for this graph, if you put 2 plus 1 into quantum computer 100 times, you will only get 3 for 80% of time, so 80 times. And the other 20 times, you'll get either 1, either 2, 4, or 5, which is the incorrect answer. And so this is the nature of quantum computers. This is not because the algorithm is wrong or not because quantum computer is erroneous. It's just the natures of the quantum computers. So it will return probabilistic curve. And that's the reasons why quantum computers, it's called probabilistic computing machines, because it returns both correct and incorrect answer, with the former has a higher occurrences. So obviously with the correct algorithms and correct hardware and all. So this is the second properties of quantum computers. And the third properties of quantum computers is called entanglement. So basically you can link 2 or more qubits together. And the reason why this important is, well, this is much less obvious than the other examples, but basically entanglement allows you to, for example, entangle these 2 balls, let's say. These 2 balls has the same properties. They're both red, and they're not, right now they're entangled. And let's say you send one to Tokyo and send the other to Jakarta. And obviously, as arrived, they're both red. But someone named Alice in Tokyo performed some alterations to change the color of the balls that she has to become blue. And basically, entanglement allows the transfers of the alterations performed by Alice in Tokyo to the qubits that is in Jakarta. So qubits that is miles and miles away, the alterations performed by Alice will also reflect it to the qubits that is in Jakarta. So this is what entanglement means. Basically, these 2 are connected, no matter if one is being altered, the other will also be altered. So this entanglement. Well, the coding of the quantum computers is still very far away from the coding that we're used to classical computers. Like if you're using Python or C++, those are very, very high level languages. And quantum algorithms today are mostly gates. And basically, when you think about AND or not gates in the classical computers, those are the units that we're currently using for coding the quantum computers. So here you have basically 3 qubits. And then for each qubits, there are different gates. You can imagine this like an AND gates or gates or not gates. And these gates will perform different alterations to the qubits here. And then you can read it from left to right and up to down. So basically, this is the starting point. And as the times goes on, as the time evolves, basically the quantum state will evolve following this trail. And lastly, you perform some measurement and you get the answers that, hopefully the answers that you want. And this is, by the way, is the search algorithms that I mentioned that increase the size, let's say, increase the amplitude of the correct answer. And because we have superpositions, we're allowed to have 8 balls at the same time, let's say. So 2 to the power of 3, 8 balls at the same time, so we can just examine them all together. And basically, as I mentioned also about the probabilistic nature of quantum algorithms, this search algorithm increase the likelihood of the correct outcomes to be observed. So this is a quantum algorithm. And the outcome is something like this. So as mentioned, the output will be something like a distribution curve, and these are all 8 poles that we've already observed at the same time. And we found that the 0, 1, 1 state is the correct answers, at least when we're using this search algorithm. So the art of quantum algorithm is to increase the likelihood of the correct answers to be observed. And so the next questions will, well, when to use quantum computers? So from the previous example, you obviously want to use them when you're searching for something on a database. But for something like 2+1, I think classical computer is better because it'll return 100 of times the correct answer, 100% of times correct answer. And so quantum computers will not be better than classical computers for all problems. Well, what kind of problems will the quantum computers good for? Well, 4 of them are listed here. There are other problems that can be solved using quantum computers as well, like optimizations. But the ones that's listed here is, the first one is cracking encryption keys. The algorithm is called Shor algorithm. Database search, which is essentially this one. This is Grover. The algorithm is called Grover algorithm. And simulating quantum system, for example, for quantum chemical calculation. And the last part I will argue is machine learning. Excuse me. So yeah, I think quantum computers will also be extremely useful for machine learning. And because we mentioned machine learning, I would like to introduce a little bit about machine learning and AI and how the trends are in the latest of machine learning and AI research. Well, obviously, some of you have been using AI in your lives today, whether it's work or whether it's personal. So, for examples, this is what ChatGPT outputted if I ask it to explain the fields of quantum machine learning with both text and pictures. So this ChatGPT GPT 4.0. So AI models like large language models, image generative models, video generative models have become quite prevalent today, and we've been using it a lot actually. Well, at least I have been using them. And at the heart of these AI transformations is something called transformer. A transformer is just basically an architecture for deep learning. And the most important, well, one of the most important part of this transformer is something called this multi-headed self-attention. So this is where the attention words come about, right? Multi-headed self-attention. Basically, the self-attention mechanisms is at the heart of the transformer architecture. And well, what does it do? What does self-attention do? Well, for language-related tasks, say we have the following 2 sentences. So the first sentence is, I like banana and I like apple too. The second sentence is, I like Samsung and I like apple too. Well, obviously, we human beings understand that. Well, for this one, the apple means the fruit, and this one, the apple means the company. But the problem, you see the problem here. You see that the problem is that the same word can have multiple meaning based on the context of the sentence. So attention mechanisms try to solve the above problem when processing words using AI for language tasks. Well, how do they do that? Well, first thing first, AI sees every word as a set of numbers. So something, for example, banana here is represented as 623. This is just a random value that I just picked randomly. And Samsung here is represented as 815. So AI sees every word as this type of, of data. And at the beginning, the AI will give the same value for both April, so 394, for example. And what self-attention allows the AI to do is basically self-attention updates each vector, so this is called vector, by incorporating information from all other vectors. So basically, the AI will update this apple from 394, for example, and based on banana, the new vectors will be 913. Is the updated value of the apple, which is a fruit. And for this app, the AI will update it so that it becomes 825. And you notice that this one and this one is much closer in terms of distance. So this apple is much closer to Samsung rather than to banana. So this is how the AI integrate context of the sentence using self-attentions that allows the updates of these vectors for each words. And so basically, yeah, the self-attention mechanisms enables each vectors to be updated by considering information from all other vectors. So this allows the model to capture the dependencies and relationships between the words. But self-attention is not the only attention mechanisms in town. You have also other types of attentions, one of which is mentioned here. It's called channel attention. The channel attention is an attention mechanism for image processing. So let's say you have this picture, this color picture, and the most standard channel that can be described here is the RGB channel, red, green, and blue channel. So basically, if you take this picture and you only take the red component of it, this will be the picture that you get. And if you take this picture and you only take the green element, this will be the picture, and the blue element is this picture. So now from one picture, you have three pictures. And then, well, for each pictures, weight will be assigned to, for example, make decisions whether for a self-driving cars to go or to stop during the red lights or during the green lights. So channel attentions allows these different priorities. So for example, when you're in traffic or when dealing with traffic lights, probably the red channel is much more important than the blue channel, because if it's red, you're going to have to stop because otherwise it's going to be a problem, right? Whether, well, at least in our traffic here in Japan and back in Indonesia as well, there is no blue whatsoever. So you can think about it that the weight for the red channel will be much higher than the weight of the blue channel, because the red channel is much more important. And so this is one of another attention mechanisms for image processing, and it has been reported that using this type of simple weighting, prioritizing, we can increase the performance of the AI quite significantly. And so, yeah, that's basically the machine learning and AI. Basically, there are these new mechanisms called attention mechanisms that's been powering today's AI, both self-attentions, but also channel attentions. Not only self-attentions, but also channel attentions. Now, on the next part, on the next couple of slides, I will introduce a little bit about quantum fields and quantum computing, especially, and how does the field interact with machine learning or AI. So these brief introductions to quantum machine learning or AI. Well, first thing first, well, what's wrong with today's AI? There's nothing wrong about them. It's just very hard to train them. So these red dots here shows the performance of supercomputers with different timeline, basically, right? We're here in 2020. Well, I don't have the points for 2024, but basically last year, the performance of supercomputers is 1E, I don't know, 24.5 coping operation per month. So every month you can produce this number of operation. Well, what about the number of floating operations needed to train this AI? Well, until recently, until ChatGPT actually, the number of training required for this AI has been basically in the linear trend with the same trend as the supercomputers. But after the applications of ChatGPT, basically, it's been extremely hard train today's modern AI. So for examples, the 2023 ChatGPT, I don't know, like GPT 3.0, something like that. It take around 10 months to train this model using the best supercomputers in the world. Because, just by the floating operations for training and against the floating operation per month. As the future AI technology requires computing capabilities beyond today's best supercomputers. That's the point of this graph. And well, for
Gekko,
those,
sorry, I have a
yeah,
question. Can you go back to the previous slide?
okay.
Yes. So from this graph, how do you get the 10 months actually?
Well, it's basically
Oh,
just,
just divide these two quantities.
yeah, just divide
Floating
these two.
operation divide. Okay.
Yes.
Good, okay. Thank you. And what does it mean to have the floating operation per month 10 to the power 26?
It's
It's huge
basically,
number.
it's well, usually supercomputers are calculated using flops, right? Floating
Mm,
operations per second. But it's very hard to make a graph that is easily observable if we're talking about flops, floating operation per second. So basically, I just make the flops into per month, and that's this graph basically.
thank you.
Mhm. Thank you for the questions. So yeah, so the point is, it's been very hard for everyone to train these AI models, and it's not only about the compute power, but it's also about money. For those with entrepreneurial spirit, this is the title of the slides. I just kind of play around the idea. So let's say, well, what's the cost of training AI models today? For example, for Llama 3 or for ChatGPT 4, this is in million US dollars. But the most expensive one, for example, is Llama 3. This is not confirmed. This is just, some people say that it's 300 million US dollar. But I think it's been a very quite good, what do you call it, unconfirmed information that's floating around the internet. So if it is so that it took 300 million US dollar, 300 million US dollar to train Llama 3, means that to train this AI, someone at the Meta, probably Mark Zuckerberg, has to pay 6.2 trillion rupiah. There's extremely expensive models that, you know, just 10% of the of cost cut down will, it can power, I don't know, it can be extremely, advantageous if you're a company or if you're a university or any research centers, for example. So from an economic standpoint, the high cost of training AI presents both a challenge and an opportunity. So quantum computers will be quite costly, at least at the beginning. But because the task itself is quite costly, it's much more costly, it might justify the adoptions of costly quantum computers. So we're trying to solve expensive problems using expensive toys, let's say. So yeah, so these reasons why I believe that from the economic standpoint, the merging of quantum computing and machine learning and AI is just a no-brainer. And well, the movement towards such future is actually has been started. For example, IBM has quantum-centric supercomputers. So these are basically the usual supercomputers supercharged with different quantum processing unit or QPU. So basically, they're trying to get the best of both worlds. If you're trying to solve 2 plus 1 equal 3, just use the classical computer. But if you're trying to solve database search or you solve the crack encryption keys, let's say, you're going to use the supercomputers, the quantum computers. And so this new breed of hybrid quantum classical supercomputer has already arrived, and they merge the best of both worlds. And the reasons why we want these hybrid classical quantum supercomputers is, as mentioned, because quantum computers is not going to be best at everything. It's going to be only better than classical computer when the problem size is large enough. So this graph shows the problem size on the x-axis and the time required to solve that problem when using classical computer and using quantum computers. Obviously, the lower the time, faster it is, the better. And as you can see here, for small problem, classical computers outperforms quantum computers. But for larger problem, for problems larger than this crossover, let's say, point, the quantum computers will be better than classical computers. And that's the motivations for hybrid classical quantum supercomputers. If the problem is small, you use classical. If the problem is large, you use quantum computer. And well, the next questions will be, well, why use quantum computers for machine learning or artificial intelligence? And the simple answers to that is because machine learning and artificial intelligence utilize these operations that is quite hard to solve on classical computer. So, for example, some of the operations that is often used on machine learning or AI models are Fourier transform, and this obviously matrix vector multiplications, solving linear equations, eigenvalue decompositions, and gradient descents, etc. And this is just the computational cost. The computational cost is shown here, and the cost when running these operations using quantum computers is shown on the right side. So it's quite hard to understand. So that's the reason why I have this graph with me. So log n is this one. And I don't know, like order n or order n squared are this one. So this is calculation cost. You see, by using quantum computers, for some operations that is often used in machine learning or AI models, we're going to be able to push down the cost when compared to the classical computers. And this is the motivations why we want to have the field called quantum computing, quantum machine learning, or quantum AI. And well, I will ease myself into quantum neural networks. So we have all seen this promise about quantum AI or quantum machine learning, or at least the reasons why we should at least um, try to explore this area. There's an economic background as well as just purely scientific background. But what is quantum neural? And on the backbones of every artificial intelligence is a neural networks. And the first step towards that future is to understand quantum neural networks. And quantum neural networks is basically the quantum versions of today's neural network. Well, first thing first, I will introduce the classical neural networks. And so this is not quantum neural network. This is just classical neural network. So classical neural networks called perceptron. Well, this is classical neural. The units that compose of that's going to compose that becomes artificial neural networks is called perceptron. So this is basically artificial neuron. And we have neuron in our brain. So this is the neuron cell in our brain. And so this is the perceptron, which is the artificial neuron that we have been using in a lot of these AI models. And if you connect a lot of these neurons, you're gonna have neural networks. And if you connect a lot of these perceptrons, you're gonna have this artificial neural network. Well, what if we scale up more and more? Well, if we scale up more and more neural networks, we're gonna have our brain. And if we're going to scale up these artificial neural networks more and more, we're going to get GPT, GPT-2 or GPT-3. Right now it's GPT 4.0. So this is basically how machine learning and AI is basically built in our image, kind of, because it utilizes the calculations, let's say, or at least the unit cell that exists in our biology. And quantum neural networks is the reflections of these classical neural networks, as shown in the previous slides. The quantum neural networks consist of parameterized quantum gates. So you can change the parameters of these gates as you train the neural network. And, well, sorry about this. And yeah, basically after you change the gates and you optimize it, you're gonna have to measure it. And after the measurements, you're gonna get the outputs, such as shown previously. You're gonna get these distributions of output of all possible outputs. And then using classical optimizer, using, for example, gradient descent, you're gonna have to update these zetas. And this loop is basically the training of the quantum neural networks. Well, the problem with this approach is that with our current quantum computers, training QNNs is very expensive. So you have to, for each parameters, you're gonna have to call the shots. Let's say you're gonna have to use the quantum subroutine here. And this is extremely expensive today. And improvement on accuracy also requires for practical applications to compete with the classical machine learning and AI models. So what I've proposed in this paper here is something called attention mechanisms for quantum neural networks. It's basically channel attention, the ones that we've already seen in the image processing slide. So, well, let's say you have these types of quantum neural network, and you measure two target qubits. The output is something like this. So there's four possible outcomes: 0, 0, 0, 1, 1, 0, and 1, 1. And this is the output. And what channel tension does is basically, well, you have these other qubits that is not going to be used during the measurement because you only need these four variations. What if we use these unused qubits, we measure them, and we create different channels? So we call this attention qubits, and this one are target qubits. Attention qubits, target qubits. What we want is the answers to the target qubits. But by measuring a new qubits called attention qubits, based on the measurements results of the attention qubits, if it's 0, then we have this uh, diagram here. If this 1, then we have this other diagram. So we can basically make a channel, just like the RGB channels that we've seen in the image processing side. And just like the classical channel attention, we can put different priorities, weights on each channel, and we can sum it up together, and we can just use softmax to return it into proper probabilities, probabilities distributions, basically. And so this simple idea, measuring one more qubit or two more qubits, but let's say just one more qubit, allow us to define new channels and allow us to implement the channel attention mechanisms to the quantum neural network. And the first problems that I've tried to apply this idea to is the quantum face recognition problem. So, well, basically, based on the quantum effect at the microscopic level, different states of matter will be observed. For example, if you have these different parameters in magnetic fields or pressure and temperature, some materials will show a metallic-like properties, and some will be antiferromagnetic-like properties, and so on and so forth. And so this is important for the development of high-temperature superconductor, for examples, or topological insulator, and obviously for quantum information and computing as well. And we classically solve these problems of QPR, which is basically, given a quantum state, determine the phase of the system. So basically, well, classically we solve this problem using this workflow. So given quantum state, we estimate the ground state, whether it's using DMRG or diagonalization. And then we perform direct measurements of order parameters. And based on order parameters, we determine quantum phase. And the challenge of the problem with this classical approach is that it struggles with high dimensionality and entanglement, obviously, because, well, entanglements cannot be, a classical computer cannot handle entanglement and dimensionality, as you've seen previously. It grows with exponentially for quantum states. And the idea here is to use quantum machine learning, well, quantum computer in general, but especially quantum machine learning to determine a quantum phase. And so this is the direct comparison of quantum phase recognitions of this 1D cluster Ising model. If I'm not mistaken, I think it's 1D cluster Ising model of 9 spins. And the task is where is to well, given these parameters here, given a set of parameters, determine whether the quantum phase will be either SPT or non-SPT. SPT is symmetry protected topological. And this is the answer. So this is small enough, so it can be solved using classical computer. And if you solve using classical computer, this will be the answer. And if you use quantum machine learning, quantum neural network without attentions, well, it's still, you can still somewhat differentiate between the SPT and the non-SPT region. But if you use attentions, the accuracy will increase quite dramatically, even with only one attention qubits. And now the answers pretty much look like the correct answers that is solved using using diagonalizations. So you see here that with attention, quantum neural network is going to be able to solve the problems very accurately. And this is just another like different graphs that shows the same fact basically. So here we differentiate the number of attention qubits from 1 to 3 and 5. And you see here that, well, obviously with the increase with attention qubit, the performance is improving. But the biggest leap in accuracy improvement is already achieved using only one attention qubits, which is great, right? We don't want to measure a lot of additional qubits. So one attention qubits is enough to improve the task to improve the accuracy for solving the task of QPR problems. And if you see the training curve as well, using attention qubits here, the blue ones, the red ones, compared to when not using attention, the black ones, the channel tension reduces the number of training epochs. So basically, it'll be much more easier to train this model. And well, QPR is quite a niche problem. So I would like to show you another application for this tension mechanism. For a very general problems that we've already been using, for example, is image generation. So image generation is basically if you ask this, I don't know, like ChatGPT, for example, can you produce an image of horse, for example, and ChatGPT will give you an image of horse. So that's image generations. And well, let's try this using quantum neural networks. And this is quantum neural networks only, and this one is with our attention mechanisms. And the problem is still extremely simple. It's just generate 0 and generate 1. And as you can see here, if you don't introduce these attention mechanisms, the 0 and the 1s that is required is not, yeah, you kind of can figure out that it's 0 if you look close enough, but it's not good. But if we introduce these attention mechanisms, the generated 0 and 1 resembles what we kind of used to when we're talking about 0 and 1. So you see here that attention mechanisms improve the accuracy of the image generations when using quantum neural networks as well. So that's basically the conclusions of my talk. So the intersections of quantum computing and machine learning AI. Machine learning and AI represents a highly promising and dynamic field of research. And for my own research, classical machine learning concepts, such as attention mechanisms, can be strategically adapted and integrated into quantum machine learning frameworks, offering novel approaches and improvements. And specifically, channel attention mechanisms have shown potential in enhancing the performance of quantum neural networks. And continued research efforts are essential to fully harness the capabilities of quantum machine learning and driving advancements in both theoretical foundations and practical applications. So that's all from me. Thank you for your time and attention.
Thank you, Gekko, for very nice talk and very interesting and pedagogical. For me, myself, I'm not a specialist in quantum computers and stuff, but I'm probably 80%, 90% understand of what you are saying now. That's really good achievement. Okay, so actually we have one question. So let's switch some language first, so to Indonesian.
Okay.
Ada pertanyaan dari Pak Chesnan ya. Apakah ada requirements khusus bagi quantum machine learning atau quantum classical neural network ya, QCNN, yang memastikan outperformance ya terhadap classical computers? Itu ada di chat. Silahkan, Gekko.
Terima kasih untuk pertanyaannya. Uh, belum ada yang bisa menjawab pertanyaan itu. Jadi uh, field ini masih lumayan baru, jadi belum ada orang yang sudah memberikan definitive theoretical explanation kenapa quantum machine learning atau quantum neural network akan lebih baik daripada classical neural network. Dan ya, jadi itu jawaban saya yang pertama. Jadi belum ada theoretical foundation yang menerangkan bahwa quantum neural network akan lebih baik daripada classical neural.
Mungkin gini ya, kita kan sekarang ada dalam era NISQ. Jadi basically quantum computer itu masih qubitnya sedikit, kemudian yang healthy qubit juga nggak banyak gitu ya. Yang maksudnya nggak yang gampang terkena dekoherensi gitu. Jadi secara praktikal berapa sih at least jumlah qubit gitu? Misalkan tadi kan kamu bilang scalingnya itu sekitar log n atau kuadrat dari log n gitu. Itu pasti kan n-nya juga termasuk di dalamnya ada jumlah qubit ya. Kalau mau be useful itu harus berapa gitu kira-kira healthy qubit itu.
Hmm. Kalau healthy qubit meaning logical qubit ya. Kalau untuk problem yang well, let's do this, man. Well, kita kita punya image 4K. 4K itu apa? 4.000 kali 3.000, something like that. 7. Kalau kita embed itu ke semua ke quantum computer as one factor, dan itu what? 20 nolnya berapa tuh? 4 sama 3 ya. 4K, 4K, 4,000. 4,000. No,
10 juta.
6. Mhm. 6 zeros. And log 10 to 6 zeros are 6. And we're talking about log 2. So 6 times 3. So 18 or 22 or something like that. That's for 4.000 kali 4.000 ya. Jadi ada juta kan. Log log 10 dari juta itu 6 kan. Tapi quantum computer itu log 2, bukan log 10. Jadi 6 kali sekitar 3 atau 4. Jadi sekitar 24 atau
24 qubit ya untuk
20 qubit.
untuk log
Jadi
image
misalkan
processing
untuk
4K gitu ya.
Ya, jadi itu hanya general idea untuk untuk masalah quantum qubitnya, hardware from the hardware point of view.
Oke. Apakah ada lagi pertanyaan? Kalau nggak, saya ada pertanyaan dari slide 28 tadi. Ya, saya dari slide ini agak ada pertanyaan tiap slide-nya kayaknya gitu. Sorry.
Oke.
Oke, di
Ya.
sini kan saya sebenarnya belum mengerti ya di mana kelebihan dari attention qubit. Kalau saya lihat graf-grafnya ini, oke, pertama dia menambah channel, oke. Kemudian akhirnya dapat graf yang purple itu. Tapi kalau saya lihat graf purple itu kurang lebih sama dengan yang atas itu.
Mhm.
Tapi sebenarnya apa yang dilakukannya? Dengan softmax itu ngapain terus supaya jadi probabilitasnya lebih bagus? Di sini aja dulu coba.
Ya, jadi di sini idenya itu bahwa dengan bikin different channel, bikin channel yang berbeda, kita bisa prioritize channel yang menjawab problem yang kita lagi coba untuk solve ya. Jadi kalau channelnya udah ke average kayak gini, kita udah nggak bisa prioritize channel, for example, yang merah atau yang biru tadi untuk image processing. Tapi kalau kita bisa pisahin channelnya, terus kita bisa prioritize pakai parameter W ini, kita bisa untuk certain problem, kita bisa prioritizing zero channel, or kita bisa prioritizing one channel. So yeah, basically channel attention ini memberikan uh,
Konteks gitu.
kayak mikroskop. Kalau kita
Hmm,
ngelihatnya terlalu jauh, kita kita nggak dapat what do you call it, fine details of the sample, for example.
hmm,
If you zoom
oke,
in, then you can see that different parts have different things. So this is the idea of tension qubits, and this is the idea of channel tension.
oke, great. Tapi waktu kita melakukan attention qubit itu ya, mengukur ya di situ. Apakah kita sebenarnya nggak
Mhm.
membuat membuat state-nya collapse itu di tengah-tengah gitu?
Hmm, Kita bisa bawa ini ke belakang karena
Nah, oke.
awalnya ini cuma buat apa, perbandingan antara uh, figure A
Mhm,
sama figure B, tapi kita
oke,
bisa measure ini di belakang.
oke. Oke. Itu berikutnya ada pertanyaan dari Pak Ridwan ya. Apa Gekko aware dengan paper yang barusan muncul di archive dari Shanadutin ya? Judulnya Better Than Classical, Subtle Art of Benchmarking Quantum Machine Learning Models. Gitu. Silakan kalau ada komen dari paper itu.
By Maria Scott, ya. Ya, saya sadar dengan paper itu. Jadi emang lumayan susah untuk membandingkan in general. Tapi saya sebenarnya uh, udah siapin untuk theoretical explanations on why channel attention works. Jadi kita theoretically show bahwa dengan channel attention itu kita bisa bikin uh, model ini jauh lebih ekspresif ketika dibandingkan dengan uh, quantum neural network only. Pas saya submit ke PRA juga ini dipertanyakan ya, karena apakah ini cuma buat problem QPR tadi, apakah ini cuma buat quantum neural network yang desainnya kayak gini. Tapi kita theoretically have shown basically that this approach is indeed increase uh, the expressive ability of the quantum neural network. So this one is theoretically proven. So the quantum neural networks compared to with and without channel tensions is theoretically proven that with channel tensions is better. But whether quantum neural network will be better compared to classical neural networks, that's a different story. So that's a
Sorry,
different type of bet.
sorry, di sini kita tahu betternya itu dari mana ya?
Okay, so uh,
Faktor apa?
basically, mhm, kita proof bahwa ketika kita pisahin channel ini terus kita kasih weight ke tiap channel, kita proof bahwa quantum neural network dengan channel attentions meng, bisa meng bisa bisa estimate any operator basically. And yeah, the whole concept is quite long to explain. So the first thing first, QCNN itu operasinya kayak gini ya. Terus QCNN itu akan mengapply this gate to this psi in and zero ancilla qubits, for example. So these ancilla qubits are the attention qubits that we've talked
Oke.
previously.
Saya tadi juga mau mikir ancilla qubit itu sama berarti ya dengan attention qubit ya.
Iya,
Oke,
kita
oke.
bisa
Qubit yang nggak dipakai
pikir
untuk ngukur
attention.
sebenarnya kan.
Iya,
Hmm,
iya.
hmm.
Sebagai attention qubits can be ancilla qubit, but it doesn't have to be. Can also
Oke.
be these qubits as well. But for theoretical explanation, it's much more easier to just use ancilla. And so basically, this is the zero states of ancilla qubits. This is the input quantum state, and this is when we apply UQCNN into everything, and then this is basically what we are going to have, right? Based on this measurement, the states of the ancilla qubits. If this is zero, then the applied gate will be U00, and if this is one, then the applied gates will be U10. If this is two, and so on and so forth. So basically, well, first thing first, you've already got the sense that by using this ancilla qubits, we're going to apply different gates into the quantum state. So you've already got the sense that this will be better than a fixed UQCNN. But furthermore, if we use this channel and then we optimize it, the weights here, then the operation is going to be like this. WK is basically this weight. So kalau if the ancilla qubits is measured at zero, it's going to be W0, U00, U00, and if it's one, and it's going to be one, and it'll be summed into the number of attention qubits that's being measured. The therefore channel attentions on QCNN is construed as a process that calculates this operator.
Saya mau tanya sedikit tentang softmax itu ngapain sih sebenarnya softmax kok bisa
Ah,
memperbaiki itu tadi?
softmax itu cuman mukul jawaban supaya masuk ke antara 0 sama 1 doang sih. Supaya jadi probabilistic
Oke.
aja.
Hmm.
Softmax-nya ini nggak terlalu. Jadi karena kita kasih weight di sini, yang purple ini nggak jadi probabilistic ya. Ini jadi kayak bisa jadi 2 atau bisa jadi 5. Terus softmax itu basically just normalize
Oh, kita
the
itu cuma
distribution.
normalisasi gitu ya?
Ya, ya, ya.
Oke, oke.
Ya.
Oke. Itu ada juga Pak Jesnan nge-share paper gitu ya. Apa ya tadi? Quantum convolution neural networks are effectively classically simulable.
Yeah, by
Ah,
Marco Cerezo. Ya, we
oke.
that's like itu kayak bulan ini gitu ya. Jadi pas kita ngerjain ini kita belum tahu bahwa quantum convolutional neural network akan classically efficient untuk di reproduce. Tapi idea channel attention ini bisa dipakai untuk quantum neural network in general because our theoretical work doesn't limit the neural networks to quantum convolutional neural network. Ya, sayangnya aplikasi kita pakai quantum convolutional neural network. Itu benar, benar apa kata Bapak?
Terus tadi bisa nggak pergi ke quantum face recognition tadi?
Oh, masih
Nggak.
lumayan jauh sih. Mhm.
Oh, nggak, maksud saya
Uh,
saya mau tanya di situ. Saya belum nggak ngubungin dengan konteks ini. Slide berikutnya kayak 29. Bisa lihat. Ah, oke. Di sini itu D itu maksudnya apa ya? State D itu.
face apa?
state D di bawah itu ada gambar yang di tengah itu
Ah,
ADN
oh ini sih,
FD itu.
ini cuma mau nunjukin bahwa dengan different parameter dia bisa
Mm-mm,
mungkin jadi antiferromagnet atau
mm-mm,
D ini sebutnya saya nggak terlalu tahu sih apa ya.
mm.
Quantum critical matter,
Oke, jadi
probably.
itu
I don't
quantum
know.
criticalnya ya. Oke, jadi
Ya,
transisi dari antivero
ya.
ke normal metal kali gitu ya.
Mhm,
Oke.
mhm.
Nah, waktu mungkin di slide berikutnya berarti ya, yang ada SPT tadi ya. Nah, oke.
Ah, ah.
SPT itu dari Hamiltonian ini gimana cara menentukan dia itu dapat SPT? Apa ada kayak semacam topological invariance-nya gitu ya, yang bisa keluar?
Ya, di sini jadi caranya kita dapat ini, dapat zoo ini, kita dapat figure ini, uh, kita calculate the ground state using diagonalizations. Uh, Terus abis itu kita ukur order parameternya. Kalau order parameternya, jadi ada paper yang udah menjelaskan gimana caranya men-solve uh, this icing model. Kalau order parameternya lebih kecil dari ini, itu akan jadi non-SPT. Kalau order parameternya lebih gede dari ini, akan jadi SPT.
Order parameter
Jadi
itu mengukur entanglement juga ya?
ya, ukur entanglement. Well, saya
Biasanya,
kurang,
biasanya kalau sistem yang
hmm,
topological itu dia entangled gitu. Itu
ya, ya, ya,
yang punya
ya,
yang punya topological order dia biasanya entangled gitu.
hmm, ya, order parameter, ya. Mungkin informasi tentang entanglement juga ada di
Oh, sorry.
order parameter.
Di slide sebelumnya kamu bilang kalau entanglement itu juga masalah gitu ya di tadi intinya ini. Itu ada high
Ah,
dimensionality
ah.
dan entanglement. Itu maksudnya gimana sih entanglement itu jadi masalah di classical
Oh,
QPR?
hmm.
Apa maksudnya
Mungkin
kalau dia makin
dimensionality
kayak
aja. Mungkin
hmm,
dimensionality lebih fair ya.
hmm,
Entanglement, kalau dimensionnya terlalu gede gitu, kayak
hmm,
kayak large scale entanglementnya lumayan susah di capture.
hmm,
Tapi
hmm.
that problem is still a problem of dimensionality. Jadi mungkin lebih fair untuk just say dimensionality.
Oke, jadi masalah itu
Hmm.
sebenarnya di dimensionality tapi ya bisa
Ya,
merambah ke entanglement
ya,
atau segala macam.
merambah ke entanglement juga.
Ya, makin besar dimensinya memang makin susah dikomputasikan kan ya
Hmm,
karena
hmm.
berketerbatasan klasikal komputer untuk masukin ya inputnya ke apa quantum wave functionnya itu mini body wave function. Oke, ini pertanyaan dari Pak Ridwan lagi. Apakah QML yang dikembangkan Mas Gekko bisa dilakukan dengan tipe komputer-komputer kuantum yang beda-beda seperti quantum annealer dan lainnya yang bukan gates based?
Oh, untuk yang bukan get based, kita bisa nggak? Saya belum pernah pikir sih kalau yang bukan get based. Jadi jawaban jujurnya saya nggak tahu. Cuman hmm, teorinya nggak akan bisa extend ke non gate quantum computer. Jadi ya, saya nggak tahu itu jawaban. Terima kasih untuk pertanyaan itu. Saya akan coba untuk memikirkan jawaban dari pertanyaan.
Di sini ada ground state estimation itu pakai algoritma apa ya? Apakah itu melakukan kayak imaginary time evolution gitu untuk cari ground state-nya?
Di quantum computer,
Ya,
iya,
ground
ya
state
itu
estimation.
pakai time evolution basically, ya.
Time evolution in
Uh,
imaginary time atau enggak?
Imaginary time, ya ini
Oke,
PITE,
oke.
probabilistic imaginary
Baik.
time evolution,
Pahit
exactly.
ini. Jadi
Ya,
itu softwarenya ya dari Qmix ya.
ya, ya.
Oke, cool.
Jadi ada macam-macam sih untuk ITE, untuk imaginary time evolution. Nah, salah satu
Hmm.
yang menurut kita paling bagus itu kita PITE disebutnya,
Oke,
namanya
saya
probabilistic
saya
imaginary.
pernah mau mencoba gitu ya melakukan ini kalkulasi imaginary time. Tapi sebenarnya kan kalau apa ya, kalau kita melakukan imaginary time evolution, operatornya itu bukan operator yang apa bilang unitary gitu. Benar nggak sih? Atau
Hmm.
paham nggak kamu
Ya,
maksud saya? Kan
ya,
biasanya
ya,
kita
betul.
pakai E pangkat I HT gitu ya. Itu
Yep,
unitary karena dia
yep,
kompleks dan
yep,
tapi kalau E pangkat minus HT gitu kan nggak unitary. Itu gimana sih caranya
yep.
ngakalinya gitu?
Jadi ngakalinnya di Python kita kasih ansila,
Ansila ya. Oke.
terus kasih real time evolution,
Mhm.
terus kita pakai controlled real-time evolutions. Jadi
Hmm,
kita introduce non-unitary-nya dengan cara mengukur ansilanya.
oke.
Jadi measurement
Kayak,
based non-unitary
oke. Saya kayaknya
introduction,
pernah
basically
pernah
ya.
baca paper juga kayak gitu yang kamu bilang dari orang
Mhm.
Jepang juga. Jangan-jangan itu
Ya,
supervisormu,
ya, ya.
jangan-jangan.
Ya, jadi
Oke.
quantum computer
Hmm,
emang kalau kalau kayak gate doang itu harus unitary. Tapi kita punya banyak cara untuk mengintroduce non-unitary operation juga sih.
oke, oke. Keren. Oke. Ada pertanyaan lain? Oke, ada pertanyaan dari Pak Santana. Apakah setiap attention qubit entangled dengan measured qubit yang dipakai untuk menentukan hasil prediksi?
Hmm, tidak harus menjawab. Menurut, hmm, that's a good question. Tahu saya sampai eksperimen saya yang sampai sekarang sih jawabannya tidak harus. Tapi apakah akan jadi lebih bagus kalau kalau kita measure qubit yang entangled with the target qubit? Saya nggak tahu. Tapi sampai sekarang sih jawabannya tidak harus terlalu entangled untuk dapat improvementnya.
Cesnan tim paper lagi ya, training di quantum neural networks. Mungkin Pak Cesnan mau memberikan remarks, mau open mic, atau Gekko sendiri sudah ini
Oh iya,
beri paper. Ya, silakan Pak.
iya maaf saya cuma share paper aja karena tadi ada pertanyaan dari Pak Pak Ahmad Rihwan tentang maksudnya apakah ada kemungkinan bisa eh, di paradigma yang lain gitu. Jadi saya cuma pikir mungkin paper yang ini bisa membantu.
Oke.
Kalau misalnya dipakai ke misalnya topological quantum computer atau adiabatic. Em, karena menurut saya yang ini lebih general, nggak harus get based.
Hmm.
Tapi mungkin eh, tasnya limited. Ya, udah no. Ya itu aja. Terima kasih.
Cesnan sekarang di Monash ya, di Australia.
Iya, iya.
Oke. Silakan Gekko kalau mau kolaborasi.
Iya.
Eh, apakah ada pertanyaan? Oke, ini izin tanya tentang perusahaan atau bisnis kuantum di Jepang. Nah, ini saya juga mau tanya dari tadi ya. Semoga tidak konfidensial kalau boleh mengomentari positioning Qmix ya
Hmm.
dibandingkan dengan pemain kuantum lainnya gimana gitu.
Kita fokus ke quantum algorithm dan quantum solution. Jadi
Hmm.
pemain, well, different perusahaan-perusahaan di Jepang sekarang mainnya kayak gini. Ada perusahaan yang fokus ke quantum hardware, kayak Quantinium. Itu nggak di Jepang sih, nggak asal Jepang, cuman mereka punya anak perusahaan di Jepang, Quantinium IBM. Terus ada yang lain lagi, QERA juga ada anak perusahaannya di Jepang. Jadi mereka adalah hardware provider. Jadi mereka kasih akses buat siapa aja supaya bisa pakai quantum computer with a fee, of course. Kalau bayar ya, kalau bayar kita bisa dapat akses ke situ. Jadi ada perusahaan kayak gitu. Terus ada juga perusahaan yang kayak Panasonic atau kayak Mitsubishi Chemical yang main business mereka bukan nggak harus pakai quantum computer. Main business mereka adalah, for example, organic chemistry atau device engineering. Tapi mereka pengen mengeksplor bagaimana menggunakan quantum computer untuk R&D mereka. Nah, basically Qmix ini adalah perusahaan yang menyambungkan dua perusahaan ini, perusahaan quantum computer provider, sama orang-orang yang pengen coba pakai quantum computer, cuman nggak tahu gimana caranya. Jadi kita kasih quantum solutions dengan mendevelop different algorithm. Uh, salah satunya adalah Python, karena kalau kita pakai Python, kita bisa simulasi yang masih kecil sih, kayak benzen atau simulasi cari ground state-nya benzen atau nyari ground state-nya carbon dioxide atau something like that. Jadi kita posisi kita adalah kita nggak mau terlalu banyak nyentuh hardware-nya, kita cuman pakai hardware yang udah di-develop sama orang lain ini untuk ngasih solusi ke orang-orang yang pengen coba pakai quantum computer. Itu sih posisinya.
Spiritnya kayak gini bisa kita contoh ya Pak Ridwan. Kita bikin company di Indonesia yang fokus ke software aja. Kalau hardware kemahalan kayaknya. Tapi software kita modal otak aja bisa kayaknya. Ada lagi yang bertanya? Saya tadi agak lupa sih. Bisa share slide 31 nggak? Itu ya.
Ya, ini
Oke,
slide
saya
sudah.
lupa tadi apa.
Hmm.
Tapi waktu waktu kamu melakukan attention itu sebenarnya apa sih attention yang ditambahkan supaya kamu bisa mendapatkan mengekstrak ya SPT dengan benar itu gimana caranya? Secara singkat aja.
Hmm. Jadi tension ngasih uh, freedom, degree of freedom yang baru pertama di kedua weight ini. Jadi ini degree yang freedom yang baru. Terus satu lagi adalah kalau kita lihat quantum neural network ini semua unitary operation. Dan well, dari perspektif machine learning model, if kalau machine learning modelnya bisa both unitary and non-unitary, maka expressibility-nya akan jauh lebih tinggi. Jadi tension ini introduce dua improvement. Salah satunya adalah non-unitary to the quantum neural network. Dan yang keduanya adalah uh, higher degree of freedom dengan parameter weights ini. Jadi untuk SPT and SPT, saya pikir itu adalah the reason why uh, kita bisa differentiate between SPT and non-SPT, and also the reasons why we can generate a better picture as well. So dua degree of increase in degree of freedom and non-unitarity.
Oh, tadi kan ada permasalahan ini ya. Di apa exact diagonalization itu ada permasalahan di dimensinya gitu. Apakah
Mm-hmm.
kuantum komputer sekarang itu bisa overcome, maksudnya bisa udah outperform dari exact diagonalization yang ada sekarang atau belum?
Mm-hmm.
Ya oke, masalah dimensi kan, tapi sekarang kan qubit juga nggak punya banyak gitu, kita punya qubit
Ya,
gitu.
ya, ya. Mm-hmm.
Dan permasalahan yang Gekko sharing tadi kan masih di 9 qubit ya kayaknya kalau salah.
Ya.
Ya, itu kan gampang
Jadi,
banget kalau exact
mm,
diagonalization kan.
ya, ya. Quantum computer sekarang masih belum bisa. Kita jadi pas nulis paper ini kita membayangkan kalau quantum computer punya at least 30 qubit. Nah, kita mulai bisa lihat, uh, kita mulai bisa solve problem yang nggak bisa di solve pakai classical computer. Tapi untuk 9 spin, 15 spin gitu sih masih bisa. 15 spin mungkin masih bisa ya. Jadi kita waktu nulis paper ini bayangkan yang udah hardware yang udah lumayan besar sebagai basis of the argument. So, ya.
Yang dari Pak Yudya, spek quantum komputer sama spek classical komputer, apakah beda mas secara fisik dan arsitektur? Maaf pertanyaan newbie, ya beda. Silakan Gekko lebih detail lagi.
Ya. Jadi uh, classical computer itu pakai bits and quantum computer pakai qubits. Dan qubits itu, well, dia bisa menggunakan fenomena yang berbeda dengan bits yang salah tiga ya. Sudah saya mention di sini, pertama adalah superposition. Jadi ini dengan 2 qubit kita bisa embed 4 state bersamaan ya. Jadi ini 00 di 01, 1011. Dan kita bisa kasih itu ke sama kita bisa kasih amplitude yang sama untuk setiap state. Jadi 0 seperempat, seperempat, seperempat. Dan kalau classical computer itu kita nggak bisa melakukan ini. Karena itu kita harus kalau kita punya 2 qubit, kita harus lihat satu-satu. Kita harus lihat 00. 00 itu apa yang tadi cow ya? Oh, cow itu bukan vegetable. 01. Oh, apple itu bukan vegetable. Jadi kita harus lihat satu-satu kalau pakai classical computer. Kalau quantum computer kita bisa lihat kalian barengan. Jadi ini salah satu the reason why salah satu alasan kita mau pakai quantum bits instead of bits, right? Kita bisa harness this phenomenon that unavailable for us in classical computers.
Boleh tanya lagi nggak? Apakah kamu sekarang membuka peluang bagi orang-orang Indonesia terutama gitu ya untuk kolaborasi gitu? Atau mungkin ada mahasiswa yang tertarik mau belajar kayak quantum machine learning dan seterusnya, bisa
Hmm.
kontak Gekko misalkan untuk atau co-supervising dan seterusnya. Gimana?
Saya masih belum ada di posisi yang kayak gitu. Saya baru lulus doktorat tahun lalu. Jadi
Iya.
saya sendiri masih baby researcher. Tapi well, coba kontak saya aja, uh,
Hmm.
see what happens.
Iya.
Tapi jangan
Misalkan,
terlalu diharapkan juga, saya masih baby
oke.
researcher juga.
Misalkan topik yang tadi itu menarik ya, misalkan mencari apa tadi, QPR tadi ya. Itu kan mahasiswa bisa belajar ya tentang quantum quantum states gitu ya, kemudian ground state-nya kayak gimana. Ternyata ground state material itu ada macam-macam, loh. Ada antiferromagnet, ada ferromagnet, ada metal, dan di dalamnya ada yang topological, dan asal dia bisa reproduce saja mungkin udah happy gitu ya. Atau tambah sedikit step lagi yang bisa publishable gitu. Untuk mahasiswa. Kami kan levelnya masih kebanyakan masuk S1 ya. Gitu. Kalau kalau bisa belajar dari Gekko mungkin adalah pengalaman yang luar biasa.
Coba kontak,
Mm-mm.
coba kontak aja.
Oke, ada lagi nggak pertanyaan ya dari sini? Mungkin ya ini udah hampir 1,5 jam ya kayaknya. Kalau dalam 8 menit, kalau tidak ada pertanyaan, oke, tidak ada pertanyaan, pas. Oke, mungkin kalau tidak ada pertanyaan berarti kita tutup ya. Saya mengucapkan terima kasih banyak pada Gekko atas waktunya yang sangat berharga. Dari kesibukannya sudah meluangkan untuk bisa presentasi ke kami
Bang.
tentang ya cutting edge ya, problem yang
Nah, saya berterima
benar-benar
kasih untuk undangannya.
frontiers. Kiranya tidak tidak kapok-kapok nanti kalau untuk suatu hari nanti ada paper lagi publish kita bisa share lagi.
Boleh,
Dan selalu
mudah-mudahan
sukses untuk
dalam jangka waktu dekat.
endeavor-nya baik di startup maupun di research postdoktoralnya. Atau ada sharing kira-kira Gekko dalam 5 tahun ke depan mau ngapain atau mau bikin perusahaan sendiri gitu. Atau kebayang sesuatu.
Belum kebayang.
Oke, oke.
Satu-satu lah.
Iya, iya. Jadi Bapak Ibu sekalian terima kasih juga sudah bersama kami selalu ya dengan antusiasmenya menghadiri Kolokium Fisika Kuantum ini. Ikuti terus Kolokium Fisika Kuantum BRIN, nantikan informasi yang detailnya di halaman sosial media kami di Facebook, Instagram. Ini udah kayak iklan banget. Atau di website quantumresearch.id. Ya, eh, dengan demikian kita tutup acara Kolokium ini. Sampai jumpa di pertemuan berikutnya. Terima kasih. Terima kasih, Gekko.
Terima kasih. Bye-bye.
Terima kasih banyak, bye.
Terima kasih.